Let's see. Okay, so recording is on. This a little bit. Okay, last week we went through some background knowledge. We talked about the compiler, linker, loaders, and also two different architectures, the x86 and the x86-64 version, and also that is called the AMD 64, sorry. We talked about Linux file permissions. Also, I give you guys a homework to check what setuid programs are, and also we talked about the memory map of Linux process for 32 and also 64-bit programs. We talked about system calls. We didn't really have time to go through environment variables or share variables, I think we're not going to do that. We will skip that part. We will only discuss that when we need. But we do need to talk a little bit about basic reverse engineering. So I will use the homework Crank Me 1 to talk about a little bit about reverse engineering. So I think most graduate students submitted your homework. So I'm not sure how many undergraduates successfully cracked this one. So if you are an undergraduate and you cracked Me, could you please raise your virtual hand there so I can take a look? I think there is a place you can raise your virtual hand. Do I need to enable something for you to raise a hand, or because I do not see anyone raise a hand here? Okay, so no one finished this one, undergraduate? Anyone finish this one? No? You guys can still hear me, right? This is a problem of, okay. So this is a problem of online teaching. Sometimes I don't get feedback. Okay, let's keep moving. So for Crack Me 1, let's see what we have here. So first, we have this program Crack Me 1. We can verify if this is executable. As you can see, this is a 32-bit version of L file. And you can also use other tools like strings, with strings or string on it, which will give you the ASCII strings in this binary file. And you can actually specify how long you define a string is. Sometimes you can set it like very long, like 10. Sometimes you can set it like here, like the default one is kind of like 3, as you can see. We do not see any string shorter than 3 characters, but we do say this one is 3. And we can say there are 2. This one looks suspicious, CES security. And also there is a string that the secret you are looking for is %s. So obviously this is a format string, and you can imagine probably the program use print something, say library functions to print out the string. And also there are other tools you can use on this one. You can use an M to show what symbols are there. You can say the start function, there is a main function, there is also a decrypt function. For this one, I didn't expect you to read a lot of disassembly. Instead, I ask you, you can use Ghidra, because Ghidra has a decent decompiler. So we can say I already opened this with Ghidra, and I haven't analyzed it yet. So Ghidra will analyze this, and IDA Pro can do almost the same thing, but the free version of IDA Pro doesn't have a decompiler, so it will not generate a C code. So IDA Pro has a better disassembler, but it doesn't have a free decompiler, but Ghidra has one. Then from here, we can look for the functions. We can go to the main function, and it will generate the C code, as you can see on the right-hand side. You can see the C code here. So look at the C code. So obviously this is not a very good tool. Usually we know what is the prototype of the main function, but this one looks weird. It doesn't know the return value type, it doesn't know the second parameter. So because of this, the code it is generating is also weird. So what we can do is we can add it to the function signatures. It will give us this, and we already know what this is. So the name doesn't really matter, but just for us to better understand this, the first argument is the number of command line argument we have. The second parameter is actually the array of the arguments, the command line arguments we have. So we can do this. This works, but it's better we do this. It may generate a better quality code, I think. Continue editing. Oh, it doesn't work this way. Oh, I have to do here. Okay, I think I have to do it here. Okay, so this one is correct. This one we can do C. This one we can do, or can we do this? I'm not sure actually. No, that works this way. Then can we do this? Maybe. So we can say after we do this, the decompiler C code is also changed a little bit. And you can see there is a comparing if the command line argument is true. If it is, it will go here to check the length of P. If you double click this, you get here. So P is a string, CSE security. And then after that, it will check the string length of parameter 2.1. So parameter 2.1, we just talked about it. This is argv. So this is just argv here. So basically, we're talking about the second command line argument. So remember, the first command line argument is always the name, the path of the program itself. So the second argument is actually the program, is the parameter argument you give to the program. So this is how the program can read from its own stack and get the command line argument. Then from there, you can say there is a comparing. So those are two lengths. Compare if they match. If they don't match, we go out. If they match, then we will compare the P, which is this string, the CSE security string, with the string we input here. So this local 24 is obviously an index. So with all this kind of things, you can change the name of those parameters, the variables. So we can change this to index for you to better understand it. Then this one compares P plus 1, each character shifted to 1. Then if everything is correct, they match, they will keep going, they will go to the decrypt function. So the decrypt function, you can say here, we can click decrypt. It gives us very long names. I don't know how it works here. I think the Ghidra somehow, because of the name of the decrypt function, it searches somewhere for the prototype. Maybe search some header file for a prototype. But this is not actually the prototype we use. That's why I told you guys we can, the actual prototype of this program is just this. Then we can, so this is kind of like cipher. Then we can delete all of those. We only have one parameters, and the return value is also a pointer. So after this, you can say this is a decryption program. What we're doing is, so this is a while true, so we just do this until we break. So the cipher is a cipher -3. So, and the cipher, if you click here, no, this one doesn't give you that. We have to go to the main function. If we go back to the main function, you can see the cipher is S here. The S is also a string here. But this one is not defined as string. So we should be able to define the string somewhere. Okay, here is it. So we defined as a string, or you can say this string is GWE blah blah blah. So basically shift this. So this is like what's that called? Caesar cipher or whatever. So each character with -3, then we can get the the plain text. So this is how you solve the problem without actually reading the program, the disassembly. What else you can do is you can just, after you figure out what it does, you can just debug the program, use GDB. In GDB, you can simply call the decrypt function. Let's see if we can do that. So what we have here, let's do a GDB crack me. Then let's set a breakpoint at the main function. Then B is setting a breakpoint. Then we use R to run the program. So now we use R, we run the program. So this GDB has a plugin I installed there. As you can see, it has many different regions. Here you can always say the registers, the value of all the registers. Here is the disassembly. This one means the next instruction. This pointer means the next instruction to be executed. And here we have the stack. So this one should be ESP, I think. And after that, it's ESP +4, +8. So this is actually the opposite direction, usually how I draw the stack, right? I usually put a memory address high at the top, the memory address low at the bottom, but this one is reversed. So we are here, then we can just, I think we can just call decrypt. Now we're in decrypt. Then we just continue, I guess. Exit normally. Okay. So I'm not sure what's going on here. So when we call decrypt, it should be able to decrypt that because there's nothing else. So it may print out, it didn't print out here. Okay, so anyway, this approach should work. Let me figure it out later and tell you where is the problem. So today, we're actually talking about buffer overflow. So this will be our first session on buffer overflow. And the buffer overflow is a classic software security problem, has influenced system security many years. It's one of the most important system security problems for many years. So stack-based buffer overflow is also called a sequential buffer overflow. As the name suggests, in this attack, attacker tries to overflow the data on the stack in a sequential manner. We will spend several weeks on this topic, and I will first give you an extremely brief history of buffer overflow. Then we will say what information a C program needs to run. We will go through several examples of overflow local variables, overflow return addresses, and also overflow the saved EBP. Probably we will do that next week or the week after that. But the examples you are seeing today, I carefully designed them. So they are unlikely to occur in real life, real world code. So in the next 2 weeks, we will see more realistic examples. First of all is, and the objectives for those sessions, including you need to understand how stack works for 32-bit and also 64-bit. You will also understand why buffer overflow could be a serious vulnerability. After these sessions, you should be able to identify a buffer overflow vulnerability in C programs and also in binary code. And also after the sessions, you should be able to craft exploits to hijack the control flow of programs if they have buffer overflow. A little bit history of buffer overflow. Stack-based buffer overflow is a type of vulnerability discovered back in the 80s, actually. So it's just impossible to tell who was the first guy that discovered it. Some other attacks, people take credit for it. Some other vulnerabilities, people take credit for it, so we know. But for this very first one, the most important one, we didn't really know who was the first one discovered it. So stack-based buffer overflow played a very, very important role in the first felony conviction in the US under the 1986 Computer Fraud and Abuse Act. So in 1988, this guy, Robert Morris, who was a graduate student at Cornell, so he developed the infamous or famous Morris worm. So this worm attacks other computers in the internet using buffer overflow as one of its attack vectors. So this worm was the first computer virus or worm that received a significant mainstream media attention because it took down a large portion of computers on the internet at that time. So this guy, Robert Morris, before he became this well-known computer scientist, a professor at MIT, an ACM fellow, a very successful entrepreneur. So he was actually convicted for this incident. However, even back then, buffer overflow was kind of like dark magic. There were not many people know how to do that. And you couldn't find a well-explained document about it. Only until November 1996, you can see this article here called Smashing the Stack for Fun and Profit. So this is kind of like the first well-written tutorial for stack-based buffer overflow. So you will read this for your homework. So this is a must read. So you can see that the guy who wrote this used a pseudonym Alpha1. So you can imagine even back then, hackers, they do not use their real names. So sometimes they don't really take credit for what they do. The same thing right now, actually. And his email address was underground.org. So, but if you search this guy right now, you probably can find out who he really is. So this is the first well-written document tutorial about buffer overflow, and it's a very good read. So, as you can see in this screenshot I took from the MITRE website on common weakness enumerations, buffer overflow is still ranked #1 in 2019. Of course, the word they are using here is improper restriction of operations within the bounds of a memory buffer. So basically, it's a buffer overflow problem. Actually, we will discuss many other vulnerabilities in this table, in this class. For example, here, number 7, used after free. So free actually means the C library function free, which you do a malloc, then you do free, right? So after you're free, the pointer will point to some place that is not there anymore. But if you use after that, it will generate some unexpected problems. Also, number 8, integer overflow. We actually, in the first class, we saw that if we add 2 integers together, it may overflow. If you use the overflowed value for something like malloc, something like memory operations, it could be very sensitive. You may access places you don't want to access. Also, you can see there are many web or database vulnerabilities shown in the table. For example, number 2 is cross-site scripting related to JavaScript. Number 3, improper input validation. Number 6, secure injection. So this usually, those vulnerabilities usually will be covered in a web security class, but not this one. This one is more about binary. Okay, so that's basically the history of the buffer overflow we want to talk about, and also that's what you need to know. So now let's dive into hacking. So most of you are C programmers. For any C function, it needs many information, a lot of information at runtime. For example, any C function, it has some code. At runtime, obviously, we're talking about a binary code. Then it will use some arguments. The arguments has to be given to that function. Even the function has the same code. Each time you run that function, you may give a different parameter. The function will also return some value to the whoever is calling it. Usually, we have one return value in a C function. However, you can actually use pointers to give a pointer to the C program, and the C function can change whatever is at that location. So that's kind of like return values. Also, there are global variables that variables any function can use. There are local variables, only the functions has those local variables can use. There could also be some temporal variables. They're kind of like local variables. Also, there is a return address. After you call a function, you have to return to the function that calls it. And where is that return address? Also, to maintain those information, we have something called a function frame pointer, which could be a little bit difficult to understand at this moment, but we will talk about it later. And also, we will have the previous functions frame pointer. So all those information has to be maintained at runtime somewhere. As a C programmer, you usually don't have to think about where those information are maintained. You don't care. You just use at C level. But in this class, we have to go a little bit deeper. We need to think as kind of like a compiler developer. So where do we put those data? And there are many choices, different choices you can make. There is no one single right design. There could be many different designs. And the different architecture, different compiler, they will make different choices. We were mainly focused on the x86 and the 64-bit version. So let's start with something simple, the global and the local variables. You know the differences between global and local variables from a C developer's perspective. Local variables are those declared in a function, or you can also declare them in a block. So only code in that function or block, you can access those variables. Outside the function, the local variable doesn't really have a life. It doesn't really exist. You cannot access it. Global variables are different. They are declared from the C syntax perspective. They are declared outside any function. So they can be accessed by any function in the program. In other words, they exist as long as the program exists. You can give parameters or arguments. Actually, I'm not sure which one is correct. When we should call it parameter or when we should call it argument. So sometimes I will just use them interchangeably. You can give arguments to programs. So those arguments are kind of like local variables, because each time you give it to a function, you call that function, only that function should be able to access that. So it's kind of like a local to that function, to that specific call, right? So you can imagine how we store them probably is similar to how we store local variables, but also it depends on different compilers, depends on different architecture. So here we have one simple program. I call it a global local V. V means variables. We can compile this obviously into an L file, but let's take a look at this program. So we have a main function, a standard main function. In the main function, we declare a local variable. L means local. So I means this is an integer. So this one is initialized. That's why I call it I initialized. This one is uninitialized. So this one we need to turn this one not initialized. Then we also, after that, we print out two other global variables, which I've declared here. The first global variable is a string. I initialize the global variable. The second one is just a pointer. It's not pointing to anywhere. So basically the first one and second one, they are the same thing. The only difference is that this one, the G underscore I, it points to the string initialized. This one, G underscore U, is not pointing to anywhere when we run this program. But both of them, they are actually pointers. They themselves, they have some space somewhere. After that, we print out the address of those two local variables. After that, we call a function func with a parameter 10. In this function func, this function returns an integer and also takes an integer as input. In this function, it also has two local variables. And in this function, we print out the address of its own two local variables and also print out the address of the parameter. So let's run this program to say okay, so if we just run this program, it will just print out everything. The first one is it print out the global variable address. So you can say the global, this is a 32-bit version. Global variable is somewhere near this address, 5655. But the local variables, the main function, first one is FFFF, D0F6. So FFFF is like the top of the memory space. Remember, that's where the stack is. So this local variable is actually on stack. The second local variable is a little bit lower address than it. You can see the lower address. So which means the stack goes from high address to low address. The main function will call the function, which will have the other two local variables. The L underscore I is at the D0CC. L underscore U is at the D0C8. You can see it still goes down. But the P, which is the parameter for this function, you can see the address is actually at a little bit higher address than the LI. It's somewhere between the LU in main and the LI in func. That's where the P is stored. That's a parameter. So this gives you a brief idea of where those local and global variables are stored. In summary, obviously we store code in the .text section, and the parameters, we store them on stack. Sometimes we store them on registers. The example I just showed you, we store them on stack. We usually store the return value in one specific register, which is EAX. We're talking about the 32-bit version. And the global variables, we can store them in the .bss section or .data section. The BSS is uninitialized, .data section is initialized. Local variables, we also store them on stack. Sometimes with some optimization, we can store them in registers to make things faster. Temporal variables, the same thing. Return address, which is not the return value. This one is also stored on stack. So you can see that here we have several important information stored on stack. Parameters, local variables, return address, and also previous functions frame pointer. The current functions frame pointer, we put them in EBP. So you can notice that those four important information, they are kind of different type. Parameters are their data, right? They has nothing, usually they don't control the control flow. Local variables, they are also data, but a return address is an address. It's where we are returning to. This is like some control information, some meta information. C programmers don't really care about this. The C programmers care about parameters. They care about local variables. They don't care about return address. They don't care about the previous functions, frame pointers. However, they are all stored together on the stack, which means when the compiler was designed this way, we put different information, or we can say different two channels, the control channel and data channel, both onto the stack. So that is a huge problem because the data channel may overwrite the control channel and make the program to malfunction. That's basically the underlying reason of this buffer over problems. As you can see, a lot of data, such as this things we just talked about, they are stored on stack. And a stack is essentially a scratch memory for all the functions. And this design is used in all the modern processors, MIPS, ARM, x86, and other designs. They all use this stack design. And basically all the most popular platforms you are familiar with use this design. And some of the platforms, the stack goes from high address to low address. When we say top of the stack, it usually means the lower address because the stack goes from high address to low address. The top of the stack itself is at a lower address. The two basic operations for a stack, this is the same as what you learned from a data structure or algorithm design class. So we're talking about the same data structure stack here. So the two basic operations for it are push and pop. So push means we put something, push an item on the top of the stack. So here it means the stack goes downwards. The pop operation means pop the top item on the stack out. So the stack will be smaller with one fewer items. So there is no operations to remove an arbitrary item from the stack. Stack structure cannot do that. In your data structure class, you know a list can do that, but stack cannot do that. So to implement a stack, we will need some kind of a pointer or index to tell us where is the bottom of the stack and where is the top of the stack. And on x86, we have hardware to support that. We have special registers to tell us where is the top of the stack, where is the bottom of the stack. So this is something you need to remember. For every function here, the ESP, as you can see, the name is SP means stack pointer. So ESP holds the address of the top of the stack. It actually points to the item on the top of the stack. So if you do something like push EAX, the push is the instruction, EAX is the EAX register. It will first decrement the stack pointer, which is ESP, to 4 bytes. Then it will store the value in EAX to the location pointed by the stack pointer. If you do pop, it's basically the reverse operation. So we have to do a pop EAX. Means we want to store the value at the location pointed by ESP to EAX, then increments the stack pointer. So when we pop, the stack pointer go higher, the stack goes smaller, right? So besides push and pop, there are other instructions can affect the stack on this architecture. Call can do that. The call instruction will call a function. The return instruction will return from a function. The enter instruction will set up the function frame. The leave one will destroy a function frame. So those at least those 6 instructions will affect the stack. And we will take a closer look at how they actually do it, because this is very, very important for you to understand buffer overflow. Okay, so on the left-hand side, I draw a stack here. So remember, the stack goes from high address to low address. So right now, the ESP, the register, points to somewhere here. And there is a value X. This is a stack. We don't really care where the bottom the stack is in this case. We only know this is the top of the stack. So now we want to push something. We push EAX. So what happens is the ESP will move to a lower address, then put the value of EAX onto the stack. So this instruction itself doesn't really change the value inside the register EAX. It will only change the value on stack. So after this memory, so stack is on memory, obviously. So this memory address has the same value as the EAX register. Pop is opposite. Let's say ESP right now points to some value X here. Then we do a pop EAX. What it does, it will get the value from the stack, move it to the EAX. So this instruction changes the register here EAX. Of course, you don't have to use EAX. You can use EBX, ECX, whatever. It will change this register. It will also change the stack. It will move the ESP. The next instruction, very important for buffer overflow, is the call instruction. So here I use an indirect call example. The indirect call means the target of the call instruction is a register. So technically, if you analyze a code at statically, you do not run that code. So when you say an instruction like this, you don't really know where it is calling to, right? There are also direct calls. Basically, they are called to a specific fixed address. But the instruction behaves the same way. So left-hand side, on top, we have the stack. The stack, there are some values. And here means the code. This is a code. And top of this is a low address. The bottom of this is a high address. So we just execute a code, one instruction, push one. The next instruction we're going to execute, which is pointed by EIP, the instruction pointer is call EAX. So this is the instruction we're going to execute. So after we execute this one, what will happen is, first of all, the address after the call instruction. So after call instruction, what's the address? It's a pop. So this address, the address of this one will be pushed on stack. And also the EIP, the register, its value will be changed to EAX. So that's the two operations. The call instruction first pushes the address of the next instruction to the stack, and also move the destination address to EIP. So after you execute this, the EIP will not point to pop. The EIP will point to some value stored on EAX. But eventually, that some value may be a function and it may have a return. And when we execute the return, it will get back to here. Okay. So this brings us to the return instruction. So the same thing here. So we have our ESP pointed to somewhere on the stack. Then we have this return instruction here. After return instruction, we have a loop instruction. So right now we're about to execute the return instruction. After we execute this instruction, what happens is the value X here, which is pointed by ESP, will be put into the EIP. So this one is supposed to some address of code, supposed to be that. And also supposed to be some valid code address. And that's valid code address, or we call it return value, will be put back to EIP. So next instruction we're going to execute will be address stored here. So that's it. That's how those two instructions, which are very important, they affect the stack and how they work. There are also other instructions. For example, enter. The instruction enter is equivalent to those three instructions. They're just basically equivalent. So enter is just the first one is push EBP. Those are fixed. It's not pushing any other registers. Push EBP, then move ESP to EBP. So how to remember this? We are moving something, ESP is the top of the stack, to EBP, which means we are losing things in EBP, right? So before we lose the information in BBP, we want to save it onto the stack. That's why before this, we have a push EBP. The EBP is actually the bottom of the current functions stack. So we will save, actually at this point, it's a previous function's bottom. Okay. Then after that, we will subtract some value from the ESP. So what happens is we have the stack like this. We have some value Z, some value Y, we have some value X, and ESP points to some value X. Now we do enter. The first thing is we push EBP. So the EBP, the old EBP will be saved here, okay? The next thing, so after this, the ESP obviously points to here. Then the second instruction is move ESP to EBP. So the EBP will be updated. The EBP will point to the saved EBP. After that, we subtract some, and also at this point, ESP also pointed to it. After that, we subtract some value from ESP. Then the ESP will point to a much lower address. And usually this is the space we reserve for local variables. So the next one is leave. There is enter, obviously there should be a leave. So before that, we have EBP point to the old EBP, ESP point to somewhere very low. Then we do a leave. Leave is equivalent to move EBP to ESP. So after we move EBP to ESP, what happens is EBP points to here, ESP also points to here. Both of them points to here, points to the old EBP. Then we do a pop EBP, which means the ESP will move up 4 bytes because we popped something out. ESP will move up 4 bytes, but the EBP will be replaced by the value stored at the previous the place ESP points to. So which means the EBP were updated to the old EBP, and the old EBP is the bottom of the previous function's stack. So this is how we leave the current function and go back to the previous function. In the examples we have before, the previous function is kind of like the main function, and the func is a new function we called. The main will call func, and func, when we return this, it will go back to main, right? So those are the 6 important instructions you will say in a lot of disassembly code for the 32-bit version. The 64-bit will be a little bit different, but the principles are the same. So the stack is each function's scratch memory, and each function allocate spaces for local variables on the stack. The address of those local variables are not fixed. Think about this. For one C function, you can call it many, many times, right? You can call it anytime you want. And whenever you call it, it will have some local variables. But obviously, those local variables doesn't have a fixed address like the global variables. So we actually checked that oh, we didn't check that. Okay. So that's why if you want to address local variables, you cannot have an absolute address. You don't have a fixed address. You have to use some kind of a reference to address those variables. And we can use, because they are on stack, we can use a stack pointer to address that. We can also use, which is a ESP. We can also use a EBP to address that. So for a lot of examples we are showing here, we are actually using the EBP to address local variables. But this is more like a compiler decision. Compiler can make very complicated choices. So if in the future, in some CTF or whatever, you see local variables are addressed by ESP instead of EBP, don't be surprised. But the standard way, the simple way, the way to not confuse you usually is use the EBP to address local variables. So usually we say a function's stack frame starts from where EBP points to, and it ends where ESP points to. And we will take a look what we have there. Like I said, that this is a lot of what we're talking about here is more like a compiler decision. So you can have many different calling conventions. To call a C function, you need to give arguments and maybe other informations. And a calling convention defines who stores what information. For example, is it the caller's job to store the parameters and where to store the parameters, or it is the callee's job to balance the stack? So those are decisions the compilers need to make. In the previous code example, the main function is a caller. The func is obviously the callee. So we can design many different conventions. Basically, we need to design who will push, store what value onto the stack to call function. And there are many different choices. We will look at a very standard one. So this one is called the say declare calling convention. So if you do not, when you program say, usually you do not give any keywords to specify what kind of calling conventions you want. And this one is a default one. There are, so different compilers, they accept different keywords if you want to choose a different calling conventions. So in this standard say declare convention, the caller will push arguments onto the stack in the right to left order. So if the function has one parameter, the caller will push that argument, one argument onto the stack. If the function takes 3 arguments, then the caller will push all 3 arguments onto the stack, starting from the rightmost one. Then the caller will execute the call instruction. Remember, the call instruction will push the address of the next instruction after call onto the stack, then move the destination to EIP. So here the destination obviously is the callee. So now we are entering the callee. The callee will first push the frame pointer, the previous function's frame pointer to the stack. In the previous example, that's the main function's frame pointer, which is in EBP. That's why we always say push EBP first. Then after that, it will set up a new frame pointer, which is move ESP to EBP. Because at this point, ESP is the top of the stack. Then they want to set up the top of the stack will be the bottom of the current top of the stack will be the bottom of my function stack. That's why we have move ESP to EBP. Then it will create some space on the stack for local variables. That's why we have a subtract some numbers from ESP. It will also ensure that the stack is consistent on return. It will balance the stack. For example, since it subtracts something, then it has to add it back. But adding it back is easy if it doesn't do other things. It will just move EBP to ESP to move it back. Also, the core E will return the return value, put the return value in the EAX register. So this is a calling convention for the C declare. Okay, so this is a standard for GCC for many other compilers. For the x86, the 32-bit version of programs. So those three instructions here also is the enter instruction. They are equivalent to one enter instruction. So they are sometimes also called, this is the function prologue, because they always happen at the beginning of the function. So basically, this is how the core E allocates the stack. We will say examples later. And also, after we finish everything in that function, the function should return. And that is called the function epilogue. Usually also 3 instructions. The first 2 is also equivalent to the leave instruction. And after that, you will just do a return. So this is how the core E will deallocate its own stack. Now, let's take a look at the global variable, the global local V function again. We're going to look at the disassembly code here. The function main. So here we have the function main. So this is a disassembly of function main. It will call the function. You can say. So I didn't really give the C code of the main function, but you can say here. Here we have a call function. We are going to call the C function func. Before that, because the C function func takes one parameter, which is P here. And we're supposed to deliver that information to func by putting it on stack. That's why we have a push A here. The reason we push A because A is number 10. So when we call the function, we have number 10 there. So now we push number 10 onto the stack, then we do a call. Push the parameter, then we call. After that, what do we have? After that, we get into the function. The first thing is we push EBP, then we move ESP to EBP, we subtract 18 in hex to ESP. So now we reserve some space for local variables. Then we move A to EBP minus C. So remember, EBP right now is the stack frame for the current function, which is func. And EBP minus something means we're talking about something in this function's stack, not the previous function stack. If it's EBP plus something, then we're talking about something. In the main function stack. So then we're moving this value A is 10. A is 10 to this address. So this is actually the first say assignment here. We are initializing this local variable. So now we can see the local variable li is actually at the address EBP minus C. And we are initializing it to 10. And this initialization is at the beginning of when we run this program. The function, we call the function. After that, we do another subtract. We know the effective address of this. So know the effective address of this instruction. We're actually getting the address of this local variable, li. We get this address to EAX, then we push EAX. Why we're pushing EAX? Because we're calling another function. We're going to call the function printful here. Okay, so this call is actually calling the function printful. So the function printf, how many parameters does it take? Here we are taking 2 parameters. Yes, the first one is a string. The second one is the address, right? So which one goes to stack first? The second one. We push the parameters from right to left. So we push this address to stack. That's why we're pushing this EAX. Then we are pushing the string. So here, obviously, we're pushing the address of the string, and the address of the string is a fixed number. So here is 700. That's how we push two parameters onto the stack and call this function. Then we call printful again. Obviously, we need to push two instructions. Like we push two address parameters again. So zeros are here. We push EAX. We push 718. So this is how we are calling functions, right? So now at the end of this, we have a return 0. Return 0 means we want to get the return address, the return value back to EAX. So we have to move 0 to EAX. So here we move 0 to EAX. So after that, we just leave and return. So the main function will get the return address directly from EAX. That's how it works. Okay. So if we want to draw the stack, I really want you two guys to, how about everyone take out a piece of paper and get a pen. Let's try to draw the stack for this function. Okay. What I usually do is the high address I draw on top, the low address I draw on bottom, then I draw a box like this. Then what do we have on the stack for let's say for the printful function? The first one on the stack will be the second argument. They will have two arguments. It will be the second argument. Here is the address, so it's 4 bytes. And this one, even though it looks like a string, what actually pushed there is actually also the address. So it's another 4 bytes. Okay. After that, we have the return value, which is there because of the call instruction. The call instruction will push the return address there. Then we are in the function printf. In function printf, one of the first thing we do is we push the EBP, same as this one. We will push EBP. That's why we have a saved EBP here. Then the new EBP will point to here. After that, we will have local variables. So this whole thing, usually we call this is a function frame for the function printf. Then, so those are the addressing you can use to access different values. If you have this parenthesis EBP, means you are accessing the saved EBP. Then if you have a positive number here, it means you are accessing something at a higher address. +4 means it's a return address, this one, because EBP point to here. EBP +4 point to here, which is return address. Then if we do EBP +8, then we're talking about the first argument. If we do EBP +12 or C, then we're talking about second argument. If we want to address something like a local variable, then we will do EBP, do elective addressing here. So if you see something like this, probably we'll access some local variables. You see something like this, then we're accessing something in the previous stack function. However, the problem here is at a binary level, you don't have those prototype information. You don't really know how many parameters we are using. Okay, so sometimes when you look at this, you are just guessing. We are looking at the first argument, the second argument, but you may do something a little bit weird. Okay, so this is a summary of the x86 stack usage. If we are doing some elective indexing over EBP, like this, move EBP -8 to EX. So what are we doing here? We are actually trying to get the address. We are actually getting the value at EBP -8 to EAX. Because when we do move, we are moving actually the value there. So this is kind of like accessing a local variable, putting the value into EAX. This one is load effective address. So this one is not accessing the value at EPP -24 hex. is actually getting the value of EBP minus 24 into EAX. So it's kind of like there is a local variable at EBP minus 24, and we're not interested into the value of it, that variable. We're interested in the address of it. So this is we're getting the address of that to EAX. Then we can also do positive index over EBP. This one, EBP plus 8 move to EAX. So this is moving the first argument. Then EBP plus C, this is moving the second argument. And also there could be a positive index over ESP. So that could be the function arguments to call E as well, or just accessing something else in the previous function. Okay. So those are the answers for it. The first one is accessing local variables, negative indexing over EBP, and those two are store function arguments from the caller. So they are positive indexing over EBP. Okay. Here we have another example to demonstrate how stack works. C programming language supports recursion. Of course, many programming languages support recursion, which means a function can call itself. So, but you wonder how this is actually implemented. How could a function call itself? Because eventually you have to implement this using machine code, right? Everything eventually the CPU can only execute machine code. So here, the main function will check how many arguments you gave there. Then you are supposed to give an integer, and this program will compute the factorial of that integer. And the fact function takes the integer as input. It prints out which function it is in. It also prints out the address of the parameter. So if the integer is 1, then this function will just return 1. If the integer is greater than 1, then it will call itself here with a different parameter, which is n minus 1. So let's run this function first, then we can also debug it to get a better feeling how the stack will look like. Now we're inside this function. So if we just run it, let's give it a number 1. So it will calculate just the factorial of 1, which is 1. Then, so we are in function fact1, and the address of n is the stack address here. Let's give it a bigger number, like 3. Okay. So the first thing the program does, it will call function fact with parameter 3. And the parameter is actually this, right? It will be on stack. I showed you before. So its address is FFFD0D0. Then because it's 3, it will go to here, which will call itself again, but this time will call itself with fact2. And inside fact2, we will print out the address of n, which is at a lower address. So here we have D0, here we have B0. So after that, we will call fact1, and that is the address. Then we calculate the value. So let's debug this program to see how everything actually works. So what I'm going to do here is I will show you how to use GDB. You just do GDB, then you put the binary's name there. Now you enter here. Let's just set a breakpoint and main function, or maybe set a breakpoint at a fact function. I think it's called fact, right? Okay. Then we can run this program using R. R means run. Then we can put a parameter there. Let's put 3 there. This is how we run it. Now we're running the program, and we set a breakpoint at fact. That's why we're inside the function fact. As you can see, we are here, function fact. we're already inside it. Since we are already inside it, we can do an IR here. So we can go, oh, actually it's showing all the registers here. So the EBP we're pointing to here, which is EBP we're pointing to this, then we can examine the address there. For example, what we exam is what is EBP here? EBP is this address. Okay, copy this. Let's examine hex value this. So this one will give what the EBP points to. So EBP plus 4 should be the return address, right? So if it will be EBP, so EBP is D008 plus 4 will be D006, right? So as you can see that, hold on, we probably haven't pushed everything. Let me do a disassemble here. Oh, this function, you can say we're not using say declare here, actually. Okay, this is funny. This function, we didn't push EBP here. Oh, I didn't realize what kind of parameters I was giving when I code this. So this function, we don't really have a push EBP, move ESP, EBP there. We only have a subtract ESP. Then we are pushing ESP this one. Then we push this one. Yeah. So this one, the stack will look a little bit different than what we showed in the slides. But as you can see in the example, as you can see example here, the address will go, the stack will go downwards. However, in this function, we're not actually pushing the EBP to the stack. So it will be a little bit different, but the return address will also be put onto the stack. Okay, let's move to the next one. So here we have another example. You can say this, there's a main function, and the main function called the FP, which means 5 parameters function. And you can say this function has 5 parameters. And we can clearly say how those parameters are pushed up the stack. What we can do is we go to 5 parameters. We do object dump of this function. Yeah, here. Okay. So we have this object dump here. So this is the main function. Go back to the C code. The parameter we're pushing are 1, 2, 3, 4, 5. So we're supposed to push 5 first, 4, 3, 2, 1. That's how we do it. Let's say if it's that. So we can say in the main function, we have the prologue, we push EBP, we move ESP to EBP. And you notice that we don't have the subtract, the immediate number to ESP here. We didn't reserve anything, no covariable for the main function. Go back to the main function. Yeah, it's true. We didn't need to reserve anything. So that's why it's not doing that. We're directly calling this function FP. So we're pushing 5, 4, 3, 2, 1, and then call this function. So after that, because we pushed those 5 parameters, they are like 20 bytes, right? So the caller itself will balance the stack. The caller pushed something, it will balance some stack. That's why the caller will add 20 bytes back to the ESP after the call instruction. Then the caller will also move 0 to AX, the main function will return 0, which means in the FP function, you can say this is how we access those variables. So first we push EBP, we move ESP to EBP. Also, there's no local variables. That's why there's no local variables. So that's why we're not subtracting anything there. Then we move EBP plus 8 to EDX. So that's the first parameter, right? Which means this is 1, okay? Because this is the first parameter. This is 1. So after this instruction, EDX will have 1. Then we move EBP-C to EAX. So this is the second parameter. So EDX is 1, EAX is 2. Then we add them together. Then we get the value 3. And we save the value in EAX. I think we save the EAX, maybe EDX. Maybe EDX. We save the value to EDX. Okay. Then we move, after that, we move the third parameter to EAX. We add the 3 to EDX again, save the value in EDX. Then we go to the fourth parameter, fifth parameter, and adding them to, the last time we're actually adding them to EAX. So the reason we do this is because we are putting the return value in EAX. So if we're adding them to EDX, we need another instruction to move it to EAX. So now this one we save to EAX directly. So we don't need to move anything to EAX. After that, because we have a push, we also then we will do a pop. Then after that, we will do return. Because there is no subtract immediate number from ESP, here we also don't need to do that move ESP to EBP anymore. So this one clearly shows you what is the calling convention for this architecture. However, there are many other calling conventions available. For example, GCC provide, also other compilers like IBM usually is compatible with GCC. They provide another calling convention called the Fastcode. As the name suggests, the binary compiler with Fastcode is supposed to be run a little bit faster. So as you can see that the previous function, if we have 5 parameters, we have to do 5 pushes. And each push is from a CPU to the main memory. So it's a quite slow operation. This is actually related to side channel attack, because if we can infer how long it takes to do some operation, we can infer what that operation is. So in this faster call conversion, the parameters passings are not based on stack. The first and second parameters do not use a stack. They will simply store those parameters in registers ECX and EDX. So everything happens inside the CPU. If you only have 2 parameters, it only happens inside the CPU. It doesn't go to the main memory. So it's a little bit faster. It's also not necessary for the callers to push those parameter onto stack, and also it's not necessary for the call E to retrieve that back from the stack. Stack is memory itself. Registers are much faster. Reading registers are much faster than reading and writing to memories. So this will make programs much faster. But if there are more than 2 parameters, you still need to push those other parameters onto the stack, simply because the x86 architecture doesn't have many registers. So in this week's homework, one of the tasks for you to do is compile the global local variable function using the fast call attribute. I think I gave you, let me check. I'm not sure it's a fast, which one is it? Yeah, should be the global one. Let's say global. Oh yeah, as you can see here, the make file. So I will give you this. In the make file, there is a main. There are 3 different targets. One is called main. One is called main fast. Another one is called main 64. So in the homework, you're supposed to compile main fast, and the difference is here I define a macro called fast, and you are supposed to get the disassembly of that and compare the main and main fast and tell me what's the difference. If you check the say source code here, you can see I define this fast macro here as this attribute fast. So this is how, if it's fast, this fast call is defined as this attribute fast call. Otherwise, it's just nothing. So that's why if I define fast here, it will compile this as a fast call instead of a say declare call. So you will say the parameter, how past parameters will be different. You need to compile that and show me in your homework. Okay, so the 64-bit version of the coding conversion is also much different from the 62-bit, simply because we have many more registers in the general registers in the 64-bit version. Remember, I showed you guys this picture for x86, the 32-bit version. We only have EAX, EBX, ECX, EDX, EBP, ESP, EDI, ESI, and EBP, ESP, usually you do not use them for some general computing. So basically you only have 6 registers to use. But if we're talking about 64-bit version, look how many more we have. We have RAX, 2 of those, then we have R8 to R15. So we have 8 more general purpose registers for you to use. So if we have more registers, then we just use it, as long as we can make the program run faster. So for the 64-bit version, usually the default Linux convention is to put the first parameter in EDI, second in RDI, second in RSI, third one in RDX. So if we go back to that 5 parameter, so I think I have something here. Okay, so this one, if you check the makefile, we can say the FP64 is the 64-bit version of the same program. If we just do an object dump of it, then we go to this function. As you can see here, we're still pushing RBP. We're still moving our SP to RBP. So obviously, these are 64 bits, not 32 bits. They are 8 bytes, not 4 bytes. Then we're moving EDI to this memory location. This is a stack. This is a minus. So this is like a local variable place, right? Obviously, this is not a very smart program because they already have everything in the register. They should not move them back to stack. This is not a very smart compiler generated code. But as you can see that the parameters were actually not on stack. Okay, stack. If you use parameters on stack, it should be EBP or RBP plus something. Here is minus. So here is moving EDI to a local variable address. So this is like a temp value. So EDI, ESI, EDX, ECX, R8D, R8, right? So you can see the last one is R8, the 6th one is R. Here we're only using 5. So we're actually moving them to a stack, to a local variable. That can be saved. Because I guess that's because I used the optimization 0. Let's take a look what kind of optimization I used here. Yep, I used the O0 there. Maybe we can, let's try to change that. Let's change that. Let's use some optimization here. Okay, let's make this again. Let's make FP64 Now we are using optimization level 2. Let's check the code again to see if it's a little bit different. Oh, see, it's much different now. The parameters are actually saved in EDF, in those registers. Then we're directly adding them together. We're now moving them back to stack. That's not necessary, right? That's kind of, it's not a very smart compiler decision to make, right? So everyone see the difference here? So with different optimization, you can see, so this one obviously will be much faster than the 32-bit version of the program, because we're not using memory at all. Everything happens in the CPU. Okay, we already say this one. So the 64-bit version of the stack usage is also similar. To access the local variables, we will do RBP minus something. To access the function argument, we will not do RBP plus something anymore. We will just use those special registers. And also, if we want to set up parameters for the core E, if the caller wants to set up the parameters for the core E, we are simply moving things to the register. We don't need to push them to the stack. So that's why you can see the 64-bit version can be much faster than even for the same program, can be much faster. Okay, so with those background knowledge, we are ready to do some buffer overflow. Before that, let me check the attendance. I will give you guys the link here, and you can put your name down. Now we have 33 people here. How do I get that? How do I get the chat box here? It's not coming up for me. How do I get a chat box? Click here. Chat. No, chat is something here. Oh, it's here. Chat. Okay. Oh, I see some questions here. Anything important? Is this something like when you call decrypt function? Yeah, you should be able to call it. I don't know why it was not showing there, but it should be a tiny issue somewhere. Okay, let's move to, yeah, let me remove this one. This is not real name. Let's move to the real buffer overflow. I will give you another 20 seconds to finish that attendance check. Okay, now I think you have a pretty good understanding of how function frame works, how stack works, but you need to do a lot of hands-on practices to understand it better. Also, like how I draw it, I want you to draw the stack like how I draw it, so you can clearly understand what's going on. Okay. It's time to look at our first stack buffer overflow example. In this example, we will only overflow a local variable. There are many things we can do with buffer overflow. We will start with something simple, then gradually move to something much more difficult, which also means we will learn how share code works. After that, we will also learn how to defeat those kind of stack-based buffer overflows. So this stack-based buffer overflow sometimes is also called sequential buffer overflow, because you are seeing in a moment. We can only overwrite things sequentially in most cases, especially the most vulnerable programs we are familiar with. So here we have a lot of program. We call it overflow local. I call it a overflow local. So this is a program. So the program, we have a main function. it will check if there are two arguments. If there are two arguments, we will call the vulful, which means the vulnerable function. So this function takes two parameters. The first one is an integer. The second one is the command line argument you gave to the program. Okay, what does that mean? That means you can give anything to it because this is the data you control. This is user control data, and the user could be malicious, which means this data could be malicious. And this program is directly using this malicious data. Then in this vulnerable function, first one, we have a local variable j, which will be assigned to this value I. Then we have a buffer, which is supposed to be a string, and it has 6 bytes. It has 6 bytes in the C code. It doesn't necessarily mean its size, its distance to the stack bottom is 6 or 10 in this case, because compiler may add some paddings there. So those are something you don't really know in the C level. You have to figure it out at the binary level. Then after that, we have a string copy. And the string copy will copy the data you gave there, which is a command line argument you gave there, copy that to the buffer. So the problem here is the data, the string you gave could be longer than 6 bytes. So when it's longer than 6 bytes, what will happen? It will overflow this, right? So j is a local variable. Its value in this case is 0. When you overflow it, it will be a much bigger value, bigger than 0. Then after the string copy, we have a condition to check if j is 0. If j is 0, we will go to printf I pity the fool. If j is not 0, we will what? We will print out a secret. So this is just a secret. So the goal of this is just to print out this is a secret. So let's see how it works. So this is a very simple buffer overflow, but you can overflow local. Okay. So here we are. We're overflowing local. We have a 32 version and 64 version. So we have this this program. If we run this program, we do not give any parameters. It will just return. Doesn't give anything. So if we add something, okay, that's 4 bytes. It will say I pity the fool. So it will show up this. It will go here. Okay. So overflow this is super easy. If we do 6 bytes, we still cannot overflow it. But if we do 7 bytes, it will overflow. When we do 7 bytes, this buffer will overflow this local variable, making it not 0 anymore. Then it will print out the secret. Okay? To understand exactly how it works, let's debug this. Let's debug this. Then let's set a breakpoint at the vol function. Let's do it at the main function. It will be clear to you. Then we run this. Let's give it 7 characters. So this is how we run it. Now we're in the main function. Let's see what we're doing. The main function so if you want to step to the next instruction, you just do ni, means next instruction, or si if you want to step in. So in this case, there's nothing to step in. Step in, for example, if it's a call, it's a jump. It's a call, you can step in. So right now we're here. We're subtract ESP4. Oh, by the way, this is Intel syntax. This is not AT&T syntax. I didn't really bother to fix that. Now we go here. And now we are here, move EX, and we just do it, doesn't matter. Then we're comparing the EAX with number 2. And the EAX, what is that? It's from ECX, it's pushed here. So this one is a different order. So this is move ECX to EAX. So, oh, we do not see the code. We do not see the code, what happens here. Let's see, okay. Okay, here we can see it. So ECX, at the beginning, the ECX is the address of the ESP plus 4. In this way, in this one, oh, hold on. Are they changing ECX again? No. Okay. So anyway, we are getting the number of, we're getting the first argument of the main function here. So we compare if it's 2, and it is 2, which means we are giving 2 arguments. Then after that, there is a conditional jump. If it's not equal, it will just jump out. Otherwise, we will do this. Now we're moving EAX plus 4 to, we move EAX to this. Then we add EAX 4 here. So these are not very important for our function. So here we're pushing EAX. So this is a second parameter of this one, which is the string, right? So which means now you can say, what's the value of EAX? EAX is this value, which is what? Which is the address on the stack. And at this address, we have the string, this. So this is basically the loader put our string onto the very top of the stack and tell the main function. This is the second command line argument. You have it. Then we push 0 because we have the first argument is 0 here. Then after that, we will call that variable function. So we do a SI to enter that variable function. So now we're in the variable function. The first one, then we do push EBP, move EBP to ESP. Okay. So let's take a look at the stack of this one. Okay. So right now we already moved the ESP to EBP. So EBP right now points to the old EBP, and the ESP also points to the old EBP, and the ESP points to here. So this is EBP. This is old saved old EBP. Then plus 4 is so this is plus 4. So hold on, this one is the address of, so this one is 0. So what's this one? So what is EBP plus 4? Why this looks weird? So this is the address, the actual address of EBP plus 4. See, this is D8, this is DC, so this is plus 4. Then DC plus 4 is E0. But the value looks weird. What's that value? Any idea here? Anyone remember what is EBP plus 4? What is at EBP plus 4? EBP points to the old EBP. EBP plus 8 points to the first argument, which is 0. EBP plus C points to the second argument, which is the address of the string. But what is EBP plus 4 here? What's this?
Previous function frame?
No, the previous function frame is here. This one is the previous function frame. This one.
Oh, okay.
Yeah.
The return.
The return address. Yes, you're right.
The return address. Yeah.
That's a return address. So when we are here, the debugger doesn't really know this is a return address. It tries to interpret this as a what? As a string. That's why we get this weird string and we don't know what this is. What we can do is we can examine this address just a hex value, and we put this address, we put this stack address here. So by doing this, we're examining what is actually at the address. So what do we expect? We expect the return address in the main function, right? Because we are in the variable function, which is called by the main function. eventually we have to return to the main function. So we expect the address somewhere in the main function. So it should start with something 5655, right? So we examine this, then we get this. See, this is the address 56556236. Okay, so what we can do is we disassemble main. When we disassemble main, we get the disassembly main. And when did we call variable? Say here, we call the variable, right? Here, we call the variable. And the next instruction is 56556236. And this is supposed to be the return address after we call this function. And this is actually what we pushed onto stack. See that? This is what we pushed onto stack. And just coincidentally, this is a readable string. 56 is 6 in ASCII. 55 is just a B in ASCII. Oh, I guess it's a reverse order actually. 36 is 6. 62 is B. But you get the idea. That's why we have the stack. What we have is this one is a saved EBP. EBP points to save EBP, and this one is EBP plus 4, which is the return address. This one is EBP plus 8, which is the first parameter. This is EBP plus 2, plus C, which is the second parameter. After that, it's actually not our, has nothing to do with this variable function anymore. It's something the main function or anything before that saved onto the stack. Okay. We can do a backtrace here to show how do we get here. See? So how do we get here? The program started with calling the loader will call the start function. The start function, the underscore start function, the underscore function will call libc start main, and eventually the libc main will call our main function. Our main function called the variable function. This is how we get here. Okay. So now we go here. We go to the more function. We keep going. This one we're moving EBP plus 8 to EAX, which is moving the first parameter to EAX. So after this, EAX is supposed to be 0, right? So EAX is 0 after this. After this, we're moving EAX. We're moving EAX to EBP minus C. Okay. What is EAX again? EAX is I. So obviously we're moving I to J, right? So now we know J's address is EBP minus C. Okay. After that, we do a lot of subtract. Now we push EBP. Why do we do a push here? Because we are going to call this function. This function has 2 parameters. The second parameter will go there first, then the buff, right? So we will push that string there. Then we'll load effective address EAX EBP minus 12. So what is this one? This one is buff, okay? Which means buff's address is EBP minus 12 in hex, and J's address is EBP minus C, right? So how much difference between there? So 12 is what? 12 is F after 2. So exactly 6 bytes, right? So you can see that the buff variable here is exact 6 bytes. That's why anything you overwrite there will get into the variable J. Now we know the effective address, we push this. Now we call this string copy function. Okay. After string copy, let's exam. So exam. So what do we have? We have EBP minus C. Okay. So what is EBP minus C again? That's the local variable J. It's supposed to be 0, but now it's not 0 because we put 770, which is this W. This W is 77 in hex. We overwrite it. If we do a string and EBP minus 12, we get this string. And this is now 6 bytes, instead it's 7 bytes. Okay, does everyone understand how this one works? This should be supposed to be a very simple buffer overflow. Give me some feedback. If you have any questions, ask now. No questions? Okay, so this one is too simple. Okay, so you can see the problem here is actually the function string copy. The function string copy, even though the buffer we have is 6 bytes, the string copy function doesn't really care about that. It will copy whatever you gave it, as long as it doesn't reach 0. So this is a string copy function. It's not secure. You're not supposed to use this function anymore when you program in C. And this is one implementation of it. You have a destination, you have the destination pointer, you have a source pointer, and for each character at a source, as long as it's not 0, you just copy it to destination. This is how you implement the string copy. Of course, this is not really a very good implementation. There are better implementations where you do not really use any special case testing criteria actually test if this one is 0. A better implementation is just something like this, just the 3 line of Sequential. This is what Niners towards like. I watched a video talk he gave. He specifically mentioned that whenever he codes, he wants to code something like this instead of something like this. He doesn't want there to have any special tests or special cases like this. But they are equivalent code. If you compare them, if your compiler is smart enough, it may generate the same code anyway. Okay. So I have some animations for how this works, but with that demo, you probably already understand. So let's say we have a push EBP here in the val function. So we will put this old EBP onto the stack. Then we move ESP to EBP, so both of them point to here. Then we subtract this. So the ESP pointed to here, EBP still here. Then after this, we move the I to EAX. So EAX is this value. Then after that, we move minus this one to EAX to this. So we are actually putting I to the local variable J. So J will have 0 as well. After that, we subtract another 8 bytes here. After that, we push EBPC, which is this P, to the stack again. Then we load the effective address of EBP minus 12. That's where the buffer is. So now we know buffer is here. It's only 6 bytes. J is here. And after that, we will push EAX. And EAX is the address of this buffer. So this variable points to here. And the ESP also points to here. After that, we call this function. And the vulnerable function, sorry, this one is string copy. Now we call string copy. And because of this, we can overwrite everything above this. Okay? We cannot only overwrite this variable J, but for this purpose, we only need to overwrite this. After that, we can overwrite the saved EBP, we can overwrite the return address and everything above that. So you can see how powerful this is, especially if we can overwrite the return address. But today, probably we don't have enough time to get there. So after this, we balance the stack. Okay, so here we have the 64-bit version of it. It's actually similar. It has the same problem. It's the same code. It's just a 64-bit version. You can see we push RBP here, move RSP to RBP. We reserve some space here. We move EDI, which is the first parameter, to a local variable. Then we move the second parameter, which is the address of that string, our command line argument, to another local variable. So we know this address of this address is since it's EBP minus, so this is a local variable, which is actually this local variable, right? Which is J. So this one is J. We move 0 to J, then we move EAX to EBP minus 4. What is this doing? EBP minus 4. Why we're doing this? Okay, I'm not sure what we're doing here. Maybe clear later. Then we move this EBP. So this one, because we're string copy here, right? So this is a second. This is the second parameter. The second parameter is stored here locally. Then we move that to EDX. The EDX to ESI. Obviously, they should do a smarter instruction where just move this to EDI instead of having two instructions. Then this one we're getting the address of buffer. As you can see here, the address of buffer is EBP minus A, and the address of J is EBP minus 40. Okay, so it's still like 6 bytes. What is 14 minus A here? 14 is 20 bytes. A is 11 bytes. It's kind of like 9 bytes. I'm not sure. I'm not good at calculation in hex. So anyway, you can see we can still overwrite. So let's just try it. I'm not sure how many bytes we should give there to. So 64 version. Oh, okay. It's still 7 bytes. It's still the buffer is still 6 bytes here. Okay, so this is a 64 version of this vulnerable program. It's the same thing. Next one, let's. This one is a little bit harder. We have another vulnerable program, which is almost the same. It has a vulnerable function, but it's here I'm not giving. So here it takes argument number. In this case, it's supposed to be 2 because we're giving 2. We want to give 2 arguments there. Then J is assigned by I. The buffer is still 6 bytes. We copy our second argument to the buffer, but instead of checking if J is 0, we are checking if J is this specific value. Okay. So any idea how to? Just give me some idea. How can we override J so we can print out this secret? Any idea there?
Yeah, because can you hear me?
Yeah, go ahead.
If the J is declared right before buff, so if we overflow buff and
Okay.
next 4 we're gonna in the next 4 bit so in buff we're gonna put 10 bytes and the last 4 are gonna be 1 2 3 4 5 6 7 8.
Yes.
And in that case it passes.
Yes, we put that exact number there. So first of all, there is some tricks you want to do here, because the number you are putting here, you'll notice that this number, if you treat them as 4 bytes, obviously they are not, let's say, readable bytes, right? So it's not like you can put any ASCII in there. They do not correspond to any ASCII characters. So what you can do is you can use in Python or Perl to just print out the hex number. So what you do is you run a program and use a dollar and the parentheses to inside of that you have the Python, Perl, or what script language you use, and to print all this. So the shell will first execute this part to generate this, and it generated a string. It's not human readable. Then put this string as the second argument to this program. So this is how we are going to do it. Let's see, where are we? We're doing overflow 2. Okay. Overflow local 2. Okay. So if we just do this, we just do 6 characters. It doesn't trigger any problem. If we put more than 6 characters, for example, put 10 characters there, it still doesn't trigger that secret, but we actually overflowed that J variable. If we put more, what will happen? We will overflow the EBP, the saved EBP. Right? Sometimes we may not have problems. Say if we put a lot more, then we get. So when we put a lot more, what do we have? What happened? You get a segment fault. The reason we get segment fault is we overwrite the saved EBP. We also overwrite the return address, right? So this value somewhere there, it will be treated as a return address, and the EIP, the CPU, will execute from there. But that's a random address we put there. There is no valid instruction set. That's why when the CPU retrieve code from there, it will generate a segment code fault. Basically, it's a memory fault. Okay. So what we can do this one is, let's say we do OL2, then we do a $, we do a Python. Let's spell Python. We do a C, we do a print. Then we can do this one. Let's say we do a 12. Okay. Then we do it for 6 times. So this should not trigger any overflow. We do 10. It will trigger overflow, but not necessarily generate segment fault. We do 20. This one should generate a segment fault. Okay. So the first 6 bytes should be the buffer. So it doesn't really matter what the value is because that's not valid. Let's just put whatever there. Let's go. Let's do AA. Let's do dead beef. Right? Dead. How do I spell dead? Dead. Okay. EEF. Right. Okay. So we put a. Oh, that's not 6. Okay, we need more. Okay, then we do AA there. Doesn't really matter. Okay, this is just for fun. Okay, so those 6 bytes will overflow what? Will overflow the buffer. Then after that, we want to put the 4 bytes value there. This 4 bytes there. Okay. Can anyone tell me what to put there? Remember, this is Little Endian. So what should we do? Which one is at a higher address? This is obviously 4 bytes, right? Which one is at a high address? Is this 12 hex in high address or 78 at a higher address?
78?
Nope. This is Little Endian. So the most significant one is 12, right? The most significant one is in high address. In this case.
Yeah, sorry, I meant like what we would put first in this, like 17.
Yeah, right. Yeah. So what we want to put here is we want to put 78 here first because it's a lower address, then 56, then 34, then 12, right? So if we do this, we get this is a secret, right? This is how you overwrite this variable to a specific value. So let's do a GDB on this one again to show you how to debug this and also to show you exactly what we have. So we have this main function, we set a breakpoint main, and what we can do is we copy this one, then we do a run, we do this. This is how we give this value as a command line parameter to GDB. So we do this. What's going on? Did I make any mistake here? Oh. It is there. Should be large. Oh, OL, not OR. Okay, sorry, I typed it wrong. Okay, now we have this. We have run. Okay, now we're here. We're in the main function. Let's just go to the vulnerable function. Yes. Function. Then we continue. So we are in the vulnerable function. We just keep going. Let's get to the point where we do the string copy. Okay, now we're going to do string copy. And we know the address. What's the address for J? The address for J is where is J? Is this, right? EBP minus C. So let's examine this. Sign EBP minus C. So no, that's not J. That is J. Okay. Yeah, the J here is the argument argc, which is 2 in this case. Okay. So right now, what we're going to execute string copy. Before we execute string copy, the value of J is actually 2. Now we do ni, we execute this. Now we check the value of string copy again. See, it's overwritten. It's the value we put there. And also, if we check the, did we put a string there? Oh no, we actually put some garbage there. So it may not show. Let's show 3 of those. Minus a little bit more. Let's do, what is the address of that? 12. Okay, so you can see what we put there is dead beef. Of course, I didn't put it in the right order. We put a dead beef there, we put AA there, then we have that 1, 2, 3, 4, 5, 6, 7, 8. That's how we overwrite 4 bytes into that 6 bytes buffer. So, okay, let's see, where are we? We finished this one. So this is some command line you will use in your homework. So in your homework, there is a crank me 2. It's very similar to this one. The difficulty you have there is I'm not giving you any source code. So you are supposed to find out what value you need to overwrite and also how to overwrite that. Okay, let's move to the interesting part. So obviously, the program we just say it's very simple, and it's carefully designed. You are only overwrite a local variable, and you cannot do much damage to that. What we really want is when we try to attack system, we want to run arbitrary codes here, even remotely. If there's a remote vulnerable web server, we want to run arbitrary code on that server, which means we take full control of that computer. And also, to do that, it may take several steps. We may first get a shell first, a reverse shell that collects back to us, and we can issue all kinds of commands. So obviously, the program, the 2 examples I showed you just now, it's far away from those kind of attacks. But like I said, what important on the stack are not only those local variables, but there are saved EBP, which is the previous function's frame pointer, and also there are saved EIP, which is a return address. So if we can change the return address, then we can make the function to call whatever code we wanted to call. If we can even put arbitrary code in that address space and we call it, then we can run arbitrary codes here with the privilege of the existing program. If that program is a setuid program or of root, then which means we are running those pieces of malicious code as a root. So as you can see that in the programs we have right now, there's basically no protections to protect attackers overwrite those values. For example, let's go back to this example. Let's run it again. We just make this a little bit longer. For example, we make this, we give 4 of those, right? We give 4 of those. Right now we main, we continue, we get it to follow a function. So here, let's go directly after to the string copy. So now we're after, this is string copy. Now we are after string copy. Let's say what we have. We exam EBP. So this one, we're not getting the value of EBP. The EBP's value is this, okay? FF, CF. This is getting the memory location of this, okay? The X also always exams the memory location. So then we do this EBP plus 4, which is what? Which is a return address. You can see the return address is also, why the return address was not overwritten? Do we have any protection here? Maybe this function has a protection. Or did I give long enough? It should be long enough. Let's try. Do we get a segment for it eventually? Just continue. Yeah, there is a segment for somewhere. No, there's a. Okay. Maybe I didn't give it big enough. Let's see. I didn't. Let's continue here. Right through. We go to the string copy. After string copy, let's exam EBP platform. Okay, I didn't give the data long enough to overwrite this. So now you see EBP plus 4 is the return address. The return address is also overwritten by the value we gave there. So then we are here. By executing this instruction, we are not triggering any problems. It's just an addition. By comparing this, it's also not a problem. But eventually, we will go to return somewhere. Okay, we're almost here. Okay, now we're going to return. So return, what it does, it will just pop. So right now, the ESP should point to that value, right? So it will just pop this value to the EIP. Then let's do it. Now, the EIP value is 1, 2, 3, 4, 5, 6, 7, 8. This is what we're going to execute. Then that's just a random memory location. I don't even know if there is anything, but we can check. So if we check here, we can get, oh, this is a memory location we cannot access. So next, when we, so right now we are, where is our code? Where return? Did we already return? Yeah. So next, when we, oh yeah, we're here. There's nothing. So now we execute. It will access the code from a memory location that we cannot access. That's why we trigger the memory fault. So now we get the segment fault. That's why we generated the segment fault, and we cannot run this. Okay. So, but you can see we put a random number in EIP. What if we put some carefully crafted numbers in? Right? So this is basically what stack-based buffer overflow is. Is we carefully craft what we overwrite to. Especially we carefully craft what we overwrite to the return address, or sometimes we can do save the EBP. So the goal here is to change the saved return address to point to attacker's code. then the program will start executing from attacker's code. So this is actually a very common vulnerability in C and C++. We will use this example to show how we do that. So now this example is also very simple, but we're trying to overwrite the return address. To make your life a little bit easier, I will suggest you to issue this command to disable address space layout randomization temporarily for your virtual machine. This is not required. Without doing this, you probably still can overflow this, but you need to do a lot of guessing. So the reason we do this is because modern OS, the modern compiler, they have all kinds of security features to make buffer overflow very difficult. Some of the features are not only for buffer overflow, but also can defeat other attacks. For example, there is something called, which we were discussing 2 weeks. There is something called non-executable stack. So anything on stack is supposed to be data or address. You are not supposed to put codes there. So you're not supposed to execute any code on stack. Also, there's address space layout randomization. Each time you load the program, you put the code, your stack, as the global variables, everything at a different location. Because to hack things, sometimes you need to know exact location of where you hack, and that will make things much harder. And also there are other features we will discuss later. You can see here we have the first overflow return address example. We have the main function. The main function where, to make things much easier, the main function will print out the address of the print secret function. And then it will call the vulnerable function, which has a buffer 6 bytes, maybe 6 bytes, maybe bigger. Then it will gets buff. So gets is different from taking the parameters from the command line. So this one will take parameters from standard in, then it will return. The problem here obviously is whatever you input here may be bigger than 6 bytes, and it will overflow the return address and save the EBP of this function. And when it returns, it will not return to here, I pity the fool. It will return to another place. And our goal is to exploit this vulnerability and make it return to this print secret function. To make things easier, that's why I print out this here. Okay, any idea how to do it? Is everyone still here? Which one are we doing? Overflow return. Okay. By the way, as you can see that when I compile this program, I put all those compiler parameters, which is first of all, no optimization, no stack. This one is no stack protector. So this one will make sure that there is no stack canary generated. Also, I do a no position independent code here. Then we have the OL program. So OL, it will print out this address, right? Then we can do all strings. So this will generate a segment fault, right? Okay, so any idea how to do this? How do we call this? Our goal is to call this function. How many people are still here?
Sorry, could you repeat that?
So, say this is a variable function, right? Our goal is to, so if we do not trigger any vulnerabilities, what will happen after this for function? It will go back to here. Because the main function call this, it will go back to here, it call print. The goal is to, instead of go back to here, which print out this insulting message, we want it to go to this function. We want it to go here. How do we do that?
But you said we cannot trigger vulnerability at vuln4, right?
We can.
Oh yeah,
yeah. We can trigger vulnerability, but how do we do that? Okay, so here's the idea, right? So let's say we're in the vulnerable function. The ESP at this point point to return address. Inside that, we will push EBP, which saves the main functions, the old EBP. Then we move ESP to EBP, so both are point to here. Then we subtract 18 bytes, we subtract C. Then we know the effective address of this. So we are loading this address to EAX. Then we push EAX. So obviously that address is that's where the buffer is. Okay. Then we do get, which will have a lot of local variables, but it will make us. So this one doesn't matter. Let's see this. When we do get, it will override things. So the idea is we want to override something like the buffer. We won't override the saved EBP, but which is not important in this case. What we really want to override is the return address. Previously, this is a return address. We override it with the address of print secret. Does that make sense? So when this val function returns, it will pop this address into EIP. So we're not going to, the return address was the return address in main. So we're not going to the return address in main anymore. Instead, it will going to the return address, the address of print secret. So this is how we can trigger, we can call the, sorry, yeah. Yeah, I'm having a class. Okay. Sorry, that's my son. So that's the idea. Does that make sense? Does that make sense? Give me some feedback. Who is still here?
So could you go?
Yeah, go ahead.
Could you go back? I just had a question, I think.
Sure. Where?
Even so the before that slide before. No, the slide with the actual function.
Slide what?
So the slide with the actual function. So I think
slide with actual function, like this one.
Yeah.
Okay. What's your question here?
So at which point do we? What does so I think is gets is what overrides the buffer.
Yeah. Exactly. So gets will take input from standard in and put in buffer.
Okay,
and
so
gets is similar to.
So you're saying that we are overriding. So we're overriding. So how would we know the address of print secret again?
Oh, I actually cheat here. You can see that I printed out.
Oh, so. But that means you pretty much. Oh, all right. So you know the address. Okay. Yes. That makes sense now. Okay.
But you don't have to do this. It depends on how this is compiled and everything. Without protections, you can easily get the address of that. Yeah. But in this case, I just printed out. I cheated a little bit here. Yeah.
Got it. Yeah.
Okay. So then what we can do here is right here. It's return true. Which program is it? Oh, it's return. Okay, so it's here. We already figured. Let's see. Did we figure out the size? Yeah, we actually showed you guys the size of it, so you know how much to overwrite here. What important is here. We know gets, right? Gets will take one parameter, which is the location, the address of buffer. And from here, we backtrace. We say the location of buffer is stored in EAX. And in EAX, we have EBP minus E. So we know the buffer is actually at EBP minus E. So what is E again? What is E? F is 15, E is 14, right? Yeah. So which means we need 14 bytes here. Oh, I didn't draw that. So which means we need 14 bytes to overwrite the whole buffer, the distance between the beginning of buffer and the beginning and the saved EBP is actually E, which is 14 bytes. So we need to overwrite 14 bytes there to fully cover that space. Then we need another 4 bytes to overwrite the saved EBP. Why did I put 18 bytes here? That's weird. Oh, but I pointed here in the middle, so okay, I guess that makes sense. Okay. Then we need 4 bytes to print secret address, right? So let's try this. So this one they take input from. This one take input from standard in. So what we need to do is we need to do, let's say, Python. So by the way, I disabled address-based layout randomization. So every time I run this program, it's supposed to give me the same address, but print secret. That makes things much easier. Right? So what we do is we do a Python. We do this. We do a print. So first, we need 14 bytes to override the buffer. So we put, so the 8 doesn't really matter, that's 14 bytes. This override the buffer because we checked the buffer start from EBP minus E, which is 14 bytes. Then after that, we put 4 bytes of the saved EAX, which doesn't really matter. So let's do another 4. That's why adding them together, we have 18. Then after that, we put the address of this. Okay. So we have 2D 62 55 56. Okay. So this is basically our exploit. And we just need to pipe this into the program because the program takes things from standard in. Does this make sense to you? Does this exploit make sense to you?
Yes.
Yep.
Okay, then we just run it. See the difference? Now we call the function. Congratulations, you made it. Before that, it will always call. Before that, it will always call. Where is the program? Okay. Before this, it will call I pity the fool. After this, because we override this, it will go back. It will go to this function and print out. Oh no, sorry. This is other. That's one. That's a return 2. Okay. So this one will print out this. Go here, and this one will just exit from here. So this function will not return. This is also something interesting. Is this print secret function doesn't return because no one actually called it. Okay. If it return, if this is like everything else, if I put a return here, it may trigger some kind of unbalanced stack and eventually trigger a segment fault. So instead of triggering any segment fault, I wanted to exit gracefully. That's why I put a system call here. So the exit 0 is actually a system call. After this, the program will just exit, destroy itself. It will not return to any function here. So usually that's what we do in share code. If something doesn't happen as we planned, we do not want the program to crash. We want it to exit gracefully. So we can actually try this. Let's try this to show you guys. Okay. What we have here. Let's comment this part out. This actually may change let's make again. Now we have this. Now we do this. It has a different address, as you can see that. If we do it again to say yeah, it's the same address. Now we try to exploit this, but we change to the address 0D 620D. Okay. So this still should call the function print secret. However, after the print secret returns, because it will return, it will not call the system exit. It will return to some weird place, and it may generate a segment fault. But it still should print out these congratulations. Let's see. This is how it works. It is still print out congratulations, you made it. But after that, it will trigger a segment fault. Does that make sense to you?
Yes.
Yeah, that's why. Yeah, that's why we wanted to exit gracefully. Okay, let me change it back. Let me change it back. Then we can go to the 64-bit version of it. Okay, let's see. 64-bit version. OR 64. Okay. So the 64-bit version is actually similar, but the difference is, let's see. Okay, let's try this. I actually didn't do this. I put the makefile there, 64 version, but I didn't actually do this. Let's see if we can trigger any segment fault there. Okay. So this is the address of the program, but remember, this one is not 4 bytes. This is not a 4 bytes. This is 8 bytes because we're talking about 64 version. Let's do object dump of this one. Let's figure this out together. I didn't actually do it myself. Okay, let's say we have the variable function here. We have a push EBP, move ESP RBP, move RSP to RBP. Then we subtract this. Then we know the effective address here. So now we know buffer is actually 6 bytes here. So the previous example, it's actually 14. It's actually 14 bytes. So even though at a C level this is 6 bytes, after you compile it, it's not necessarily 6 bytes away from saved EBP. As we saw at this 32-bit version of code, it's actually E, right? So E means 14 bytes. But the 64 version of here is actually 6 bytes. Okay. So we do this, we do gets, then we override it. Okay. So I guess the script, the exploit should look something like this. First, the 6 bytes. Oh, hold on, we need to change this to 64, 6 bytes. Then we have saved the EBP. Sorry, saved RBP. So how big is that? Is it still 4 bytes?
8.
Yeah, it's 8 bytes. All right. So we have 8 here. Then the address, the location, let me save this. What is the one? We just run this again. Okay. All right, we see the address. Oops. Yeah. Oh, can I copy? I copied enter as well. Sorry. Let's do this. So what is the address here? So the low is 561140. Then 00. We do want, even though the other 4 bytes are also 0, but we do want to put 0 there because we don't know what is on the stack. If it's not 0, we may jump to a different location. 0, 0, 0, 0. Okay, let me check. Looks like it's correct. Let's see if it works. Oh, it works. So the 64 bits is the same thing, right? The only difference is the saved EBP is 8 bytes, and also the return address is 8 bytes. It may work if we only overwrite 4 bytes because the value there is a return address, and that may start with 0. So even if we only write 4 bytes, it may work. Let's see. Yeah, it works. You can say this one may work, I guess. Yeah, it works because it's just 0 there. We don't have to overwrite it. It is already 0 there. Okay. So this is how we do this one. Okay. The next one is a little bit more challenging. Where are we? Okay. The next one is a little bit more challenging. Probably we cannot finish this one. The difference here is, but I will explain how everything works. This one I call it overflow return 2. This one is actually directly related to one type of attack called return to libc attack. But before we talk about shellcode, I don't want to frame this as a return to libc attack. Actually, the first one and this one are quite similar. As you can see that we have this main function. The main function will print out the print secret function. This is what we want to call. And we have a vulnerable function, which has a buffer and has a buffer overflow problem. The difference is this print secret function will take an argument, okay? And the argument has to be a specific value. The previous one, it doesn't take any argument. What does that mean? If it doesn't take any argument, we just need to override the return address on the stack. Then we will jump to that return address. However, if this one, it takes an argument, which means even if we successfully jump to here, this function then will check the argument from the stack. It has to verify the argument from the stack. Otherwise, it will also still print out I repeated the full, right? So the challenge here is how to put the argument, put this one on the stack and where to put it. That's a difficult thing here. Let's analyze this. I guess we don't have time to finish this today, but after analysis, we will finish it this next week. And next week, we will talk about adding shellcode there. So what we have here is this function is a vulnerable get buff. And before we override this, this is the return address, this is the saved EBP, this is buff. And we can override all of this. And to call this function, obviously we still need to put the address of print secrets there. We have to put the address of this at this return address. But after we get here, what will happen? After we get here, where is the ESP? The ESP will actually point to, here. It will not point to, because those are, this one is return address, this one is saved EBP, they are balanced. So ESP will point to somewhere above here at this point. We are about to enter this program. Okay. Now we enter this program. What do we have? The program, what will it do? It will push EBP. So it will push whatever is in BP. So whatever is in EBP right now is what we overwrite there. We overwrite something here. When we get out, it was popped to EBP. Then it will push EBP, which means it will overwrite this part, which is a return address before, to the overwritten value. Then it will move ESP to EBP. So both EBP will put here. Then it will subtract something. Then where is the parameter? So EBP is here. So where is parameter? Parameter is the current EBP plus 8, right? Because plus 4 is the current function's return address. Plus 8 is the first parameter. So it will check this address for the parameter of its, the print secret function will check this address for this parameter. It will believe this address is a parameter 1, okay? But this address is also something we can't override, right? That's why when we design this, we need to override this thing, okay? We need to override buffer, the value doesn't matter. We need to override the saved EBP, the value doesn't matter here, okay? Then we need to override the address of a print secret to the return address here. So after that, we need to save 4 bytes here. These 4 bytes will be the return address for this print secret function. But because we have exit here, it will never return. So it will never use this. So the value of this doesn't matter. But this one does matter. This one, it will treat this as an integer, as this parameter 1. Of course, if this function takes multiple parameters, we can still do this, right? So this is, so we need to override the full thing to make it go into this function and call this print. So probably that's a little bit too much to digest. Anyone following here? I guess this is probably too much to digest for this class.
Quick question.
Sure.
So relative to the, let's say, to volume foo, where does the parameter, so let's say volume foo takes a parameter.
So the vol foo doesn't take any parameter.
Yeah, but let's say, so if it does take a parameter,
yes.
Where would it be relative to the print secrets parameter? Would
so, it be? So for this one, even if let's say right now we are in vulnerable foo, right? So the vulnerable foo's EBP is here, okay? EBP points to here. So its parameter will also be, the first parameter will be here, the second parameter will be here. So this is still something we can't override.
Got it. Yeah, I was so wondering, so EBP of volume foo would be at the same spot where EBP of print secret would be, or would it be a little different?
It will be a little bit different. So for volume foo, the first parameter is here. The second parameter is here.
Okay, got it. Yeah.
For print secret, the first parameter is here. The second one is here. The previous one, which is the first parameter for vol foo, will actually be treated as a return address as print secret.
Got it. All right.
Yeah. Okay. Any other questions? So this one probably a little bit harder to digest. So this is how the return to deep C works. We will study that maybe next week. Any questions? Okay, so we still have 20 people here. So today, this is our first week of buffer overflow. So I do want to get some feedback from you guys. So is it still understandable? Is everyone following? Give me some feedback. Speak, guys, speak.
Yeah, except for the last part. I think I
Okay.
need a few more read-throughs, I guess.
Okay, so you talk about this one, right? This one you don't understand, right? So everything else so far is good, right?
Yep.
Okay, so this one we will do it again at the beginning of next week. We will debug it, so you can clearly see what's going on, and we will show this animation multiple times. I probably will design another one with 2 parameters to make it even harder. Yeah. How about everyone else? So ABEC, is that how I pronounce your name? You are the one who has been asking questions, right?
Yep.
Okay, cool. So
I think I think I understood. Well, I did also have some background knowledge on this before, but
okay.
I think at least for me, probably the biggest challenge would be like replicating this in or just remembering the GDB syntax because
Yeah.
yeah,
So
that seemed to
yeah,
be yeah.
that's why I actually put all those in the slides. So for example, how do you do that? And also um, in the first class, the slides, I have some GDB tricks there. And also you can always ping me on the Slack channel to ask me questions on that. By the way, I noticed that for the first homework, many of you, when you have a question, you try to contact me directly. I would suggest you to just ask questions in the private or the open Slack channel, so I can answer those questions to everyone. And other people, if they have the same problem, they can see the answer directly. So I don't have to do that multiple times. Yeah. Cool. So let's go through the homework. Where is the homework? Where do I put it? I should have it somewhere. So for this week, the homework, I will finalize this because I was not sure how much I can cover today. First of all, is there are several blogs or whatever you need to read. Oh, there are some actually I have to remove because we didn't cover that part today. Next week, you can read the Smash the Stack for Fun and Profit because we're talking about that next week. And this week, your homework is mainly to replicate what we did in the class, what I showed you a demo in the class, because without doing it, it's always different. And also, the exploits I have in the slides may not work, or I should say, will not work on your virtual machine. Because in your virtual machine, I didn't disable address space layout randomization. So the first time you run it, you need to disable it, but you will have a different address as I have on my machine. So that's why it's perfect. You need to figure it out by yourself. You can follow the steps I used in the class, but you have to figure out the exact locations and everything by yourself. So besides replicate what I have done in the class, also you need to do that fast call one, the fast call to tell me how they are different. I guess that's it. I need to check if you can do crack me 2 now. I think you can do crack me 2, but we're not doing all of those. We're pushing those to the third week. Okay, so I will call out some names because since you guys have been very quiet, I really want to know where you are at. So let's say I don't shit. So can you unmute yourself and tell us a little bit about yourself? I think you're undergraduate, right?
Yeah, I am.
Okay, so are you following so far or?
Yeah, I have some basic knowledge, but like
Okay.
I was like, it's like pretty shallow.
Okay.
So, I need more time to review or digest tonight.
Okay. But
Like the examples, like the first and the second buffer overflow are like, they very help a lot. So
yes.
yeah.
Okay. Cool. So sounds like some of you have some hacking experience. You probably, at least in theory, you know what's going on, right? So
yeah.
okay. So the next step is just to practice. Okay. So Ed, do you want to say something?
I think I'm in the same boat pretty much
Okay.
as the last gentleman. I get the concepts. It's the fine detail and, you know, some of the syntax and things like that. What I really have to do is just review the first 2 classes, do the practice, and, you know, I'll reach out to 5 questions, but I'll try to be ready for class 3.
Okay, good.
Yeah.
How about Kamenach? There are 2 Kamenach. I'm not sure. Are you guys the same person or?
Yeah, it's the same.
Okay.
I just logged in with my PC and my mobile device.
Okay.
So I was good till the buffer overflow, the second one, and I lost track after the third one. Like I'm kind of slow, so I'll just rewatch the videos. It should be fine.
Okay, cool. So like I said, the key is I try to put this in the homework. So you guys were do the homework and replicate what I do there. The key is you need to replicate what I did in the class. So what we have this week is not difficult compared to what we are going to do in the future. So it's very important that all of you fully understand what's going on this week. Okay, I will call 2 more names. How about Michael? Michael, can you unmute yourself? Do you want to say anything? Okay, looks like Michael is not here or he is too shy. How about Phil Fox?
Hey, good evening. I feel confident about the material so far.
Okay, perfect. Okay, cool. I guess that's it for today. Just do the homework. Then I will see you guys next week.
Great. Thanks, everybody.
Okay.
Thank you,
everyone.
Professor.
See you next week.
Thank you, Professor. See you next week.